Okay, so yesterday all we did was I taught you how to draw a vector in 3 space, 2, 3, 4. And I drew this like this parallelogram like desk thing. See? But that's totally optional. That's just for perspective's sake. So we're going to actually kind of start over and just do this again. So you can pick a new spot on your graph paper. Practice drawing your x, y, and z axes. Make sure that they obey the right-hand rule. X cross y must be z. Okay? Or I should probably say I hat cross j hat needs to be the positive k hat direction. So please try to draw a right-handed coordinate system real quick. Or you can copy mine. Okay, so my x-axis, I usually actually use this for my x-axis down here. I almost always make this x and make this y like I did yesterday. And that way z points straight up the page. Like that. Okay. Notice I only put arrowheads on the positive end of each axis. Every axis has a negative direction too, but I don't typically draw the arrowhead on that end. Although I think I will go ahead and extend my z-axis to go underneath the desk, so to speak, so that there's at least a downward z also. Okay, if you want to mark off your axes now, you can, or you can do it while you're plotting the vectors. Okay, so I would like to graph the vector u, and it's going to just be yesterday's vector, 2, 3, 4. And I'm going to let you guys make up where you want the negatives, but I'm going to use the numbers 5, 6, 7 here. And let's put some negatives in. So let's put in at least 2 negatives on our vector v. So what do you guys want to use?
-3.
You want to use, okay, we put a negative in the first vector, that's fine. So -4. Make the 6 negative. Make the 5 negative. Okay, I think that's probably enough to get the point. This way we have at least a negative x and a negative y, you know. We have motions in all 6 directions. Okay, so we're going to start off by drawing what I call breadcrumbs. Okay? So for vector u, you're supposed to do a 2-space travel in the x direction. So I like to draw little dots there. They look like breadcrumbs on your journey. You drop them like Hansel and Gretel. And then 3 in this direction. And then it says -4. So starting from what looks like the point 2, 3 on the xy plane, how am I going to go -4 in the z? You're going to go down, right? So you're going to drop 4 spaces below where you're at. 1, 2, 3, 4. And the cool thing about this paper is you just literally have to count the dots. So you don't have to guess how long is 4. It's all right there. Just count 4 diagonal spaces down. Beautiful paper. Okay, now, my first vector, I will make blue. And it extends from the origin down underneath the desk towards that terminal point. So try to make the head land right on the terminal point there. This is vector u. It's supposed to look like it's pointing away from you to the right and down. Okay? Away from you to the right and down. If you can't imagine that, it doesn't matter. Just know this. That vector is probably a lot longer than your eyes are telling you. Right? Look at this stick in my room, right? I have no idea where I got this thing. But, you know, if I was looking at this like this, trying to figure out how long it was, that's kind of dumb, right? It's like, how long is that thing? This looks pretty short. Well, if I hold it that way, it's like, oh, it's long. So if I hold it this way, you can see how long it is. If I hold it this way, you're like, oh, I can't really tell how long it is. It's short. I want to hold it perpendicular to my line of sight. Right? The same thing's happening here. This blue vector is probably quite long, just may not look it. It's a perspective issue. If you really want to see how long it is, you'll have to rotate the whole coordinate system. No thanks. So just leave it and trust it. Let's go into our next vector in green. So we're going to have to count 5 spaces in the reverse x direction. So that's this way. And 6 in the... Ooh, I might go off the page here. You have plenty of space. I have to, guys, I have to change this to a positive 6. I'm so sorry, but I will go right off the edge of my paper if I don't. So I have to advance 6 spaces in the positive.
Can we make 7 negative?
You want to make the 7 negative?
Let's do it.
Fine. Okay, so I can do that. I can go down 7. So breadcrumbs, 5 left, I guess, 6 forward, now 7 down. Here we go. 1, 2, 3, 4, 5, 6, 7. This vector's hard to see, man. That thing is hiding in the back. It connects from the origin to that last point. And again, the drawing really isn't that important. But remember what I said about one of Euclid's rules. These 2 lines, the green and the blue, form their own plane. Right? They form their own plane. So we can kind of draw that plane, I guess. But I would rather not. It's confusing looking. All right. Now, let's say you wanted to find magnitude of these guys. That's easy. You just do square root of, and then for the first one it'd be 4 plus 9 plus 16. For the second one it'd be square root of 25, 36, and 49. No big deal. If you want to find the dot product, piece of cake. You would take the x's and multiply them. Take the y's and multiply them. Take the z's and multiply them. Add them all up. What would it mean if you got a positive dot product? It's the same thing I meant yesterday. What would it mean if you had a positive dot product? The angle between them is acute. It's always going to mean the same thing. What would happen if you got 0 for your dot product? What would that mean? Somehow these vectors are magically perpendicular, which is actually what happened on my worksheet. On worksheet 2, I typed it up, and I accidentally made 2 perpendicular vectors in 3 space. I have no idea how I did that. But you're going to get 0 when you do this calculation of the angle between them on tonight's worksheet. Who knew? Okay, it was an accident, actually. All right, so what's more interesting here is finding the cross product, okay, because it's going to feel kind of new. There is a third vector called u cross v, and it is perpendicular to the plane that u and v are occupying. Okay? If you can't visualize it, that's fine. We can still find it. So here's how you find it. You set up a matrix, technically a determinant of a matrix, and the top row is I hat, j hat, k hat. These guys are just like placeholders, but you need them there. And then you copy down the coordinates for u, 2, 3, -4. Those are your components, not coordinates, excuse me. And you put in v in the last row. What am I doing right now? I'm trying to find u cross v, the cross product vector. All right. Maybe you remember this from your pre-calc or your algebra 2 days. Maybe you don't. But to find a 3x3 determinant, you actually start off, I usually start off, in the upper left corner. So I write down I hat. And you actually are going to use these 4 numbers here to create one single number. In other words, you're going to find the determinant of this minor matrix right here. So you're going to do 3 times 7.
Can it be -7?
Did I copy wrong? Oh, that was going to be a -7. Thank you. Let me fix that first before we start any calculations. So you're going to take 3 times the -7, see? So the 3 times the -7. And you're going to take the -4 times the 6. And you're going to form 2 products. So that's what? -21 and negative 24. And you're going to subtract them, okay? So that's negative 21, but you're taking away negative 24. So it comes out to just simply 3. And you know what this is? This is the first component of your answer. 3I hat. 3I hat. In other words, your vector starts with 3 comma something comma something. Cool, we're a third of the way there. Next, you do the j hat. Okay? So you get in here, and you repeat this. Only now you're using the j hat. And you're not going to use the same 4 numbers as before. Does anyone know which numbers we're going to use? Yeah, you're going to actually use everything except what's in the j column, right? So you're going to use the 2 and the negative 7. You're going to use the negative 4 and the negative 5. You see? So I'll try to keep color coding. You need the 2, the negative 7, the negative 4. You need the negative 5. But that comes out to negative 14 minus 20. So this is basically negative 34. Negative 34. Hopefully I didn't make any mistakes, so you'll tell me if I do, right?
Wait, isn't it I hat, that whole thing, then minus j
Yes.
hat?
Yes.
Which means
Give me a
that-
second. I was about to get to that.
Okay.
Okay, now the tricky thing about determinants is you're supposed to alternate your signs, okay? So after you've worked with your first column, you go on to work with your second column, but there's a mandatory minus sign that pops up. And it goes right here, between these two calculations for I hat and j hat. This is really easy to forget. There's a mandatory minus right there. In other words, this is actually 34. And then I'm going to go ahead and finish it up. I need to do the k hat, don't I? K hat. Let me see if I can move this stuff here. Oh, the wonders of technology. When you run out of space, make more. Okay, so for the k hat, guess what numbers you're going to use? Everything except what's in the k column, right? So you're going to use these 4 instead. The 2, the 6, those ones. You've done this before. It's just 3 by 3 determinant. But it's basically the 2 and the 6, and then it's the negative 5 and the 3. So I'll plug in all the numbers. The 2 and the 6, the 3, the negative 5. And that's 28. So it's a 28 k hat, and that's the last component. I left my 27. Yeah, I'll learn to add one of these days. I left my middle component in red to remind you that that one is the opposite of what you got. Okay? 27. So this is the U cross V vector. And trust me, it's perpendicular to the other two, even though U and V were not perpendicular. Last comment. If you go ahead now and find the magnitude of this, that will also be important. That is the size of the parallelogram, the area of the parallelogram that is formed by these two blue and green vectors. Okay? And in that case, you can call it square units, because it's an area. So if these are length vectors, you just found the area of something, meters squared. But not all vectors are length vectors, right? Some are like velocity.